Hey everyone, welcome to Module 2 of our Irrigation Design Course, brought to you by AgriGrid. We've been in the game for over 20 years, designing irrigation systems that are not just cost-effective, but also reliable and efficient for our customers. So, you're in good hands as we dive into today's topic. Today we're talking about assessing soil for irrigation, and trust me, it's no simple task. It's a team effort, pulling in experts from different fields and digging into some pretty specialized studies. What we're going to do in this module is break down the basics, the key principles and background info about soils that you absolutely need to know when planning irrigation. Why does this matter? Well, if you're looking at a potential irrigation project, understanding the soil types on that site is make or break. It's not just about whether the system will work technically. It's also about whether it'll pay off economically. When you're designing an irrigation system, figuring out the risks and the rewards all comes back to one thing: really knowing the site and what its soils are all about. Here's the big takeaway. Irrigation systems have to be tailored to fit the soil and the bigger agricultural picture, not the other way around. If you try to force the wrong irrigation method onto a soil that can't handle it, or if you're watering soils that just aren't cut out for it, things can go south fast. And I mean costly south. But it's not just about money. Messing this up can wreck the soil itself. We're talking problems like salinization, erosion, waterlogging, compaction, or drainage headaches. Throw in low-quality water, and you've got a recipe for even bigger trouble. Now don't worry. We're not here to turn you into soil scientists overnight. That's not the goal. What we do want is for you, as irrigation designers, to see how critical soil is to the whole planning and implementation process. You've got to get a handle on these concepts and put them to work so that your systems aren't just successful, but sustainable too. That's what we're aiming for, and I'm excited to walk you through it. Let's talk about what you'll walk away with by the end of this course. By the time we're done, you'll be able to: first, explain what soil really is and why it's such a big deal for irrigation. Next, you'll get the lowdown on soil texture, the basics of what makes it tick. Then, we'll dive into soil structure and porosity. Think of it as understanding how soil holds itself together and breathes. You'll also pick up some key insights into how soil and water interact, which is at the heart of all this. And finally, we'll tie it all together, showing you how to take this knowledge and use it practically in your irrigation designs. To wrap up this module, we're going to have a Q&A session. It's your chance to ask anything that's on your mind and make sure you're feeling solid about soil. Plus, we've got you covered with a list of resources you can tap into if you want to dig even deeper into this stuff. Sound good? Let's get started. So what exactly is soil? Let's break it down. Soil isn't just dirt under your feet. It's a living, breathing system that's the backbone of life on land. It's what holds up plants, manages water, and keeps ecosystems humming. Think of it as the Earth's skin, made up of a wild mix of stuff: bits of rock, organic leftovers, air, water, and tiny microorganisms all working together. Soil doesn't just pop up overnight. It takes thousands of years to form. It starts with rocks breaking down through weathering, then mixes in decomposing plants and animals. The result? A unique blend that looks and acts different depending on where you are, thanks to things like climate, location, and what's living in it. Now let's get to the good stuff. What's soil made of? Picture it in 4 parts. First, you've got minerals, about 45% of the mix. These come from rocks like quartz or clay breaking apart, and they're what decide if your soil feels sandy, silky, or sticky. Then there's organic matter, only about 5%, but it's a powerhouse. This is the decomposed bits of leaves, roots, and critters, pumping nutrients like nitrogen and potassium into the soil. Next up, water, around 25%, which flows through, delivering those nutrients to plant roots and keeping microbes happy. And finally, air, another 25%, sitting in the gaps, giving roots and soil creatures the oxygen they need to breathe. So that's soil in a nutshell. A dynamic, living team player that's way more than just dirt. Pretty cool, right? Let's keep rolling and see how this ties into irrigation. Okay, let's dig a little deeper, literally, into how soil is put together. Soil isn't just one big blob. It's built in layers, kind of like a cake, and we call these layers horizons. Together, they make up what's called a soil profile. Starting at the top, you've got the O horizon. Think of it as the organic VIP zone, packed with stuff like decaying leaves and roots. Right below that is the A horizon, or topsoil. This is where the action happens. Tons of biological activity with plants and critters doing their thing. Next down is the B horizon, the subsoil, where minerals start piling up. Then comes the C horizon, which is mostly weathered bits of the parent rock. And at the bottom, that's bedrock, the R horizon, the solid base everything sits on. These layers aren't the same everywhere. They shift in thickness and makeup, and that affects how fertile the soil is or how well it drains. So, why should we care about soil? Because it's a total MVP in ecosystems. It's the anchor that keeps plants rooted. It holds onto water and cleans it as it filters through. And it's a nutrient recycling machine. Plus, it traps carbon, which is a big deal for fighting climate change. And get this, it's home to billions of tiny workers, bacteria, fungi, worms, and insects that break down organic stuff and keep the soil in shape. For us humans, soil is everything when it comes to food. The FAO says it's behind 95% of what we eat. It's the foundation of agriculture. But here's the catch. Soil's under attack from things like erosion, pollution, and just plain overuse. If we don't look after it, we're risking our food supply and the planet's balance. So, bottom line, soil isn't just dirt you kick around. It's alive, it's breathing, and it's holding up life on Earth. Pretty amazing when you think about it. Next up, let's tackle the basics of soil texture. So, what's soil texture all about? It's pretty simple. It's the mix of different-sized mineral particles in your soil. We're talking about how much sand, silt, and clay you've got in there. Each one's got its own vibe, and they're sized up like this. First, there's sand, the big kahuna of particles, ranging from 0.05 to 2 millimeters. Rub it between your fingers and it feels gritty. Then you've got silt, the middle child, sitting between 0.02 and 0.05 millimeters. It's smooth, almost floury when dry, but gets silky or slippery when wet. And finally, clay, the tiniest of the bunch, less than 0.02 millimeters. This stuff's sticky when wet and turns into hard clumps when it dries out. So, why does this matter? Soil texture is a big deal. It's like the personality of your soil, and it affects everything. First off, water holding capacity. Clay soils? They cling to water, sometimes too much. Sandy soils. Water runs right through them like a sieve. Silt's somewhere in between, holding a decent amount. Then there's drainage and aeration. Sand's great at letting water and air move through. Clay can get soggy and suffocate roots. Silt's a middle ground again. Nutrient retention's another one. Clay's got a huge surface area and a charge that grabs nutrients and holds them tight. Sand? Barely holds any. Silt's moderate. Workability, or how easy it is to dig into, also ties back to texture. Sandy soils are a breeze to work with. Clay? It's a beast. Rock hard when dry, sticky and heavy when wet. And erosion? Fine stuff like silt and clay can get washed or blown away easier than chunky sand. Now let's talk textural classes, the names we give soils based on their sand-silt-clay mix. You've got the sandy crew, like sand, or loamy sand, where sand's running the show. Then the clay gang, like clay, sandy clay, or silty clay, where clay's in charge. The silt squad, like silt or silt loam, leans heavy on silt. And then there's the loams, the Goldilocks of soils. Loams have a nice balance of sand, silt and clay, pulling the best from each. Think loam, sandy loam, clay loam, or silty clay loam. Just so we're clear, loam isn't a particle. It's what we call that sweet spot mixture plants love. So, that's soil texture in a nutshell. Gritty, silky, sticky, and everything in between. It's the starting point for figuring out how your soil's going to behave, especially when water's involved. On the right of your screen, you will see a commonly used soil classification chart called a soil texture triangle. It has 3 sides, each representing one of the 3 components of soil structure. Later in this module, I will show you how to use this to easily classify your soil samples. Ready to see how this plays into irrigation? Let's keep going. All right, folks, let's talk about how to figure out soil texture, something you can do yourself without fancy lab equipment. We're going to walk through 2 simple DIY methods that will give you a solid start. First up, the field test, or you might hear it called the ribbon test. It's quick, hands-on, and honestly, the more you do it, the better you get. So, for the field test, all you need is your soil sample and a bit of water. Here's how it goes. Grab a small handful of soil. Clean it up first by picking out any stones, roots, or big chunks of organic stuff. Now slowly add water to it, just enough to make it moldable, like damp putty. Think workable, not sopping wet. Knead that soil ball in your hands to mix it up well. Next, pay attention to how it feels. Run it through your fingers. What's the vibe? If it's really gritty, like sandpaper, that's a clue you've got a lot of sand in there. If it's smooth, maybe silky or even floury, that's pointing towards silt. Now, let's try the ribbon trick. Take that soil ball, put it between your thumb and forefinger, and gently push it up with your thumb to see if it flattens out into a ribbon. Here's what to look for. If it won't form a ribbon at all, or it's super weak, say less than an inch before it falls apart, that's likely a sandy soil, like plain sand or loamy sand. If you get a medium ribbon, about 1 to 2 inches, and it breaks pretty easily, you're probably dealing with a loamy soil. Think loam, silt loam, or sandy loam. But if it makes a long, strong ribbon, over 2 inches, and holds together, that's a sign of clayey soil. Could be clay, clay loam, or sandy clay. One more thing, check how sticky it is. If that moist soil is clinging to your hands like glue, that's another hint there's a good amount of clay in the mix. So, that's the field test. It's all about getting a sense of the soil with your hands. No tools, no lab, just you and the dirt. What do you think? Ready to give it a shot? Let's move on to our second DIY method for figuring out soil texture, the jar test, sometimes called the settling test. This one's a bit more visual and gives you a rough idea of the proportions so you can actually see what's going on. It's perfect for those of us who like a little show and tell with our soil. Here's what you'll need. A clear, straight-sided jar, like a mason jar or even an old pickle jar, your soil sample, some water, and a ruler. If you've got it, you can also grab a tiny pinch of non-foaming dish soap or water softener. It's optional, but it helps the clay settle out cleaner. Let's get to it. First, clean up your soil sample. Pull out any big stuff like stones or roots. Then, fill your jar about 1/3 to halfway with soil. Add water until it's about 3/4 full. If you're using that soap or softener, toss in just a pinch now. It'll keep those tiny clay particles from clumping up too much. Screw the lid on tight. And here's the fun part. Shake it like you mean it. Really go for it, several minutes, until all the soil clumps are broken apart and everything's swirling around in there. Once it's all mixed up, set the jar down on a flat spot where it won't get bumped. Now, we watch and wait. After 1 to 2 minutes, the heavy stuff, sand, drops to the bottom first. Grab your ruler and mark where the top of that layer is. Give it 2 to 6 hours, and the next layer, silt, will settle on top of the sand. Mark that level too. Then the slowpoke, clay, takes its sweet time, settling out after 24 to 48 hours, sometimes longer. The water might still look murky, but once it clears up a bit, or after a couple of days, mark the top of the clay layer. Oh, and if you see bits floating on top, that's just organic matter. Don't worry about it for this. Time to do some quick math. Measure the height of the sand layer, then the silt, then the clay. Add them all up to get the total height of the settled soil. To figure out the percentages, take each layer's height, divide it by the total soil height, and multiply by 100. That gives you the percent sand, silt, and clay. Now let's estimate the texture based on those numbers. If it's mostly sand, say over 70%, you've got a sandy soil. Mostly clay, above 40%. That's a clay soil. Mostly silt, over 50%. You're looking at a silty soil. If it's more of a balance mix, you're in loamy territory, and the exact type, like sandy loam or silt loam, depends on the specific percentages. So, there you go, the jar test. It's like a little science experiment that shows you the layers right in front of your eyes. Pretty neat, huh? Anyone want to guess what their backyard soil might turn out to be? Okay, folks, let's wrap this up with why these DIY methods, the field test and the jar test, are so handy. They give you a solid starting point for understanding your soil texture, and that's gold, whether you're gardening, farming, or making decisions about managing your land. You'll get a good feel, pun intended, for what you're working with. No lab required. Now, if you need something super precise, like an exact breakdown of percentages to plug into the official soil texture triangle chart, that's when you'd send a sample off for lab analysis. They've got the fancy tools like sieves and hydrometers to nail down those numbers with pinpoint accuracy. But for most of us, these at-home tricks are more than enough to get the job done. So, what do you think? Ready to test your soil and see what's growing under your feet? Remember this diagram? Let me show you an example of a classification based on a fictitious jar test. See the three labels on the sides of the triangle. They are labelled percent clay, percent silt, and percent sand, and each has an arrow indicating the direction it has to be read in. The triangle also has handy grid lines making reading easier. During our fictitious test, we measured a soil that consisted of 50% sand, 30% silt, and 20% clay. Let's plot that on the triangle. 50% sand. 30% silt. 20% clay. Can you see the point where the three lines intercept? Our fictitious soil sample would have been classified as a loam soil. Let's try another. A soil sample with 64% sand, 23% silt, and 13% clay. This sample would be classified as a sandy loam. Not so difficult, is it? This soil classification will be expanded on later in this series, but before we do, let's talk about soil structure and porosity. All right, everyone, let's shift gears and talk about soil structure and porosity, two key pieces of the soil puzzle that really matter for understanding how it works. So, texture, we've covered that. It's all about the size of the mineral particles, like sand, silt, and clay. But structure, that's about how those particles are organized, how they group up. And porosity, well, that's the result. It's the space between those groups that lets air and water move through. So what's soil structure all about? In simple terms, it's how those basic building blocks, sand, silt, clay, and organic matter, come together into bigger clumps called aggregates or PEDs. Here's an analogy for you. Think of texture as the raw ingredients in your kitchen. Flour, sugar, maybe some butter. Structure is what happens when you mix them up and bake them. It's the crumbly texture of your cake or the crust of your bread. It's how everything holds together. Now, how does this structure actually come to be? It's a mix of physical, chemical, and biological action working together. On the physical side, picture this. Cycles of wetting and drying make soil swell up and then shrink back down. It's like the soil's breathing. Freezing and thawing do something similar, nudging particles closer together over time. That's nature doing some heavy lifting. Then we've got the chemical processes. Clay particles and iron oxides act like a kind of natural glue. Nothing too strong, but enough to help things stick. Certain ions play a role too. Calcium, for example, is like a cheerleader for clumping, encouraging particles to bundle up in a process called flocculation. Sodium, on the other hand, is the opposite. It pushes particles apart, keeping them loose and dispersed. But here's where it gets really interesting. The biological stuff. Honestly, this is often the star of the show. Organic matter kicks things off. It's food for the microbes, and it also binds particles directly. Then you've got microbes like bacteria and fungi churning out sticky substances. Think of them as tiny glue factories producing polysaccharides to hold soil together. Fungal hyphae, those little thread-like structures, weave through the soil like a web, wrapping particles up tight. Plant roots get in on the action too. They release compounds that feed the microbes while physically prying soil apart, creating those clumped-up layers. And don't overlook the soil critters. Earthworms, for instance. They eat soil, process it, and leave behind these solid little aggregates called casts. Plus, their tunneling opens up channels through the soil. So, soil structure. It's this incredible teamwork of forces, shaping how soil holds together and functions. Pretty amazing when you break it down, isn't it? Okay, let's wrap this up with a quick recap. Here's the rundown. Texture? That's all about the size of the mineral particles, sand, silt, and clay. It's the building blocks. Structure? That's how those particles, plus some organic matter, team up into aggregates. Think of it as the shape of the crew. Porosity? That's the empty space in between, split into big macropores and tiny micropores. Good structure is the hero here. It sets up the perfect balance of porosity, giving you both macropores and micropores. That balance is what lets water soak in and drain out, keeps air flowing, gives roots room to grow, and keeps soil buzzing with life. Basically, it's the key to healthy, productive soil. But watch out, compaction's the villain. It crushes that good structure and wipes out those crucial macropores. So, texture, structure, porosity, they all work together, and getting them right is what makes soil tick. That's the foundation we're building on for irrigation. Now that I have explained the basics of soil structure, go on and complete the Q&A section before continuing on to the section dealing with the interaction between soil and water. Before we dive into the next section, let's take a quick pause to talk about a couple of key terms that are going to be super helpful for you to understand. You've already seen how soil tests can be a bit tricky to interpret. There's some wiggle room there, right? So, to make things clearer and give designers a solid way to compare soil samples, we need to bring in a few engineering calculations. These will give us some common metrics to work with. Now, we're only covering 2 of them today, but keep in mind that for a full, detailed analysis, you'd typically need to send your samples to a lab. First up, let's talk about bulk density. This is basically a way to measure how much a dried-out soil sample weighs compared to its total volume, and by total volume, I mean the volume of the sample before we dry it out. So picture this. You've got your soil sample, you dry it completely, weigh it, and then divide that weight by the volume it took up in its natural state. That's your bulk density, and it's usually somewhere between 1,000 and 1,800 kilo per cubic meter. That said, if the soil's been compacted, like if it's been heavily walked on or driven over, you might see even higher numbers. Now, a quick heads up. You might hear bulk density called by a few other names, like volumetric density or matrix density. Don't let that throw you off. They're all talking about the same thing. The dry weight of the soil per unit of volume in its natural, undisturbed state out in the field. There are a couple of common ways to measure this, like the clod and wax method, or the cylinder method. Both are pretty standard in the field. In fancy terms, we represent bulk density with a capital P and a little lowercase b as a subscript, PB. The math is straightforward. You take the mass of your dried soil sample, divide it by the volume of that sample before drying, and there you go. That's your bulk density. All right, let's move on to the second metric, porosity. This one's all about the empty spaces in the soil, the spots that aren't filled with solid particles. Think of these spaces as the tank where water gets stored for plants to soak up. Porosity is expressed as a percentage, and it tells us how much of the soil's total volume is made up of these empty spaces, or pores. Those pores can hold either air or water, depending on the conditions. Now, porosity depends on a bunch of things: the soil's structure, its texture, how consistent it is, and even its bulk density. Here's the thing though, porosity isn't just about the total amount of pore space. The size of those pores actually matters a lot more. We break pore sizes into 2 main categories: macropores, which are bigger than 60 micrometers, and micropores, which are smaller than 60 micrometers. Macropores are great for letting air move through the soil and for helping water flow and spread out. Micropores, on the other hand, are key for holding onto water through capillary action. That's the water plants can actually use. Here's a fun fact. Clay soils often have a higher total porosity than sandy soils because they've got a ton of tiny micropores. That means they can hold more water, but it also means water moves through them more slowly, and sometimes they don't get enough air. Sandy soils, on the other hand, might have less total pore space, but they've got more macropores, so they release water more easily to plants. That's why the volume of readily available water, or RAW, is usually lower in sandy soils compared to clay, even though clay holds onto water more tightly. Now, measuring porosity directly is kind of a pain. It's not something you can easily do in the field. So instead, we use a handy formula that ties together bulk density, particle density, and porosity. Here's how it works. Porosity, as a percentage, is calculated by taking 1 minus the bulk density divided by the average particle density, then multiplying the whole thing by 100. If you don't have an exact particle density for your soil, a common stand-in is the density of quartz, which is 2,650 kilos per cubic meter. Plug that into the formula, and you've got a good estimate of your soil's porosity. So, there you have it. Bulk density and porosity in a nutshell. These metrics are going to be super useful as we move forward, especially when we start designing systems that need to account for how soil handles water. Let's keep rolling. Now that you've got a solid grip on what soil is and how we classify the different types, let's take things up a notch. Welcome to part 2 of our module on soil. It's time to dig into why those classifications actually matter when we're figuring out how to design an irrigation system that works like a charm. You see, the way water and soil get along isn't a one-size-fits-all deal. It depends a lot on what that soil is made of and how it's put together. So, in this next chunk of our journey, we're going to chat about some key players that come into the mix. Things like infiltration rates, how fast water soaks in, water holding capacity, how much water the soil can hang on to, saturation point, when the soil's like, I'm full, no more, permanent wilting point, when plants start throwing in the towel because they can't get enough water, and field capacity, the sweet spot where the soil's holding just the right amount of water after excess drains off. These aren't just fancy terms to throw around at a dinner party. They're the building blocks we'll use to make smart decisions down the road. For example, that water holding capacity we mentioned. It's going to be a big deal in later modules when we start sketching out the nitty-gritty details of our irrigation system's capacity. Think of it as the groundwork for making sure we're delivering the right amount of water at the right time to keep those plants happy and thriving. Stick with me here. This is where it all starts coming together. Next up, let's talk about how water interacts with soil. It's pretty fascinating, and it all depends on the type of soil and its structure. There are 2 key ideas we need to get our heads around: infiltration and permeability. Don't worry, I'll break it down for you. So, infiltration is basically how water moves down into the soil. Think of it like water soaking into a sponge. The infiltration rate is just how fast that happens. When the soil is super dry and you first add water, it soaks in really quickly at first. But as the soil gets wetter, that rate slows down a lot. Eventually, it levels off to a steady pace when the soil reaches what we call field capacity. That's the point where the soil is holding as much water as it can without being oversaturated. That steady rate is the one we really care about. Now, a bunch of things can affect how fast water infiltrates. The soil's structure and texture play a role. Think sandy versus clay soils. Other factors like the amount of sodium in the soil, the size of the water droplets, how dense the soil is, and how much moisture is already in there, all make a difference. One thing that's really interesting is what happens on the surface of the soil. When rain or irrigation water hits the ground, the energy from those droplets can break up the soil particles and create a crust on the surface as it wets. That crust can slow down infiltration, and it's a big deal when you're deciding what kind of irrigation system to use. Here's a quick heads up. Soils that have an initial infiltration rate higher than 125 mm per hour, or a steady rate lower than 3 mm per hour, are usually not great for irrigation. They either let water through too fast or barely at all, which can cause problems. Oh, and if you're wondering how we measure infiltration, there are a few common methods out there, like the double ring, single ring, furrow, or infiltrometer. But here's the catch. Even if you test the same soil with different methods, you might get pretty different results. It's a bit tricky, but that's why understanding this stuff is so important. What do you all think? Have you noticed how water behaves differently on various soils in your own experiences? All right, let's dive into the next soil topic that's super important for understanding how water moves: permeability. I'll keep it casual and break it down for you. So, permeability is all about how easily things like gases, water, and even plant roots can move through a layer of soil. Picture it like how easy it is for water to flow through a coffee filter versus a piece of cloth. It's all about the material. When we talk about irrigation, there aren't really strict minimum values to judge soils by for permeability. But it becomes a big deal if you need to do something like leaching, where you flush out excess salts, or if you're over-irrigating and need to drain off extra water. You don't want that water just sitting there, right? Now, how permeable a soil is depends on a few things. Its porosity, how many tiny spaces it has, its structure, texture, and even how much water is already in the soil. All of these factors play a role in how well water can move through. When we zoom in on water specifically, we use a fancy term called hydraulic conductivity, or KW for short. This just tells us how well the soil can let water flow through its pores at a certain moisture level. Here's the general rule. The wetter the soil, the faster water moves through it. So, a fully saturated soil, where all the pores are completely filled with water, has a higher hydraulic conductivity than a soil that's only partially wet. Why does that happen? Well, in a soil that's not fully saturated, the water has to take a longer, more winding path through the pores to get where it's going. It's like taking the scenic route instead of a straight highway. The longer that path, the more friction the water molecules run into, which slows everything down. That's why hydraulic conductivity is lower in unsaturated soil. Here's where it gets a bit wild. In some cases, a tiny pore that's completely saturated with water can actually move water faster than a bigger pore that's only partly saturated. But if both pores are fully saturated, the bigger pore wins. It'll conduct water faster because there's more space and less resistance. Pretty cool, right? Have any of you noticed how water seems to drain differently in wet versus dry soils, maybe in your garden or a local park? To understand the interaction between soil and water, we need to talk about how soil holds onto water. It's a really cool process, and there are a couple of key ways it happens. I'll break it down for you in a simple way. First, imagine you've got soil with a layer in it that water can't get through, like a waterproof barrier. When water soaks into the soil, it hits that impermeable layer and starts to pile up, creating what we call a water table. If you keep adding water, that layer of soil above the barrier gets completely saturated, meaning there's no air left, just water. We call this waterlogged. This can happen all the time, or just for a little while, depending on the soil and the conditions. Now, the second way soil holds water is through something called capillarity, and this is where things get interesting. Capillarity is basically how soil, which is full of tiny pores, can suck up water and hold it even above the level of the water source. Like if you dip the edge of a sponge in water and it soaks up higher than the water level. The water moves into those pores and stays there, even if you take the water source away. This happens because of two forces working together: adhesion and cohesion. Adhesion is the attraction between the soil particles and the water molecules. Soil particles often have a negative charge, and water molecules are polar, so they stick to the soil like magnets. Cohesion, on the other hand, is the attraction between water molecules themselves. They like to stick together. So, adhesion pulls the water to the soil, and cohesion helps the water molecules tag along with each other, filling up the pores. Here's the cool part. Because of capillarity, water can stay in the soil even though gravity is trying to pull it down. But how tightly the soil holds, that water depends on how much water is already there. If the soil is pretty dry, the water is held really tightly, and it takes a lot of force, like a plant trying to suck it out, to get it out. But if the soil is already full of water, the water isn't held as strongly, and it can even move out on its own because of gravity. A classic way to picture capillarity is with a thin glass tube, called a capillary tube. If you stick one end in water, the water will climb up the tube higher than the water level outside. That's because the water molecules are attracted to the sides of the tube, adhesion, and they pull each other up along the way, cohesion. It forms a little column of water inside the tube, but there's a limit to how high the water can go. The cohesion between water molecules can only hold so much weight. Imagine the water molecules at the top of the column are like, "We can't pull up any more, friends." When the weight of the water column balances out with the cohesion forces, the water stops rising. That's when everything reaches an equilibrium. So, that's the gist of how capillarity works in soil. Pretty neat, right? Have any of you seen something like this in action? Maybe with plants or in a garden? Let's hear your thoughts. Another key concept about soil and water is something called the permanent wilting point, or PWP for short. So, picture this. The permanent wilting point is basically the point where the soil gets so dry that plants can't get enough water to keep up with their needs, specifically for transpiration, which is like the plant's way of sweating to stay cool and move nutrients around. When the soil hits this dryness level, the plant starts to wilt, and it's not just a temporary droop. It's permanent, unless you add more water through something like irrigation or rain. Now, plants can sometimes look a bit droopy on a hot day. That's pretty normal. It's called temporary wilting, and it happens because the plant is losing water through transpiration faster than it can pull water up through its roots. But when the day cools down, the air gets more humid, and the plant slows down its transpiration. That gives it a chance to recover, regain its turgor pressure. That's the internal pressure that keeps it firm, and perk back up. Here's where the PWP comes in. When the soil reaches the permanent wilting point, the water is held so tightly by the soil that the plant just can't pull it out, no matter how much the temperature drops or how humid it gets. The soil's grip on that water, what we call the soil matrix force, is just too strong, and the plant doesn't have the energy to overcome it. At that point, the plant is in real trouble unless you step in with some water. One thing to keep in mind is that the PWP isn't the same for every plant. It depends on the plant itself. Different plants have different needs and tolerances. For example, a drought-resistant crop like olive trees can handle a much drier soil before hitting their PWP compared to something like tomatoes, which need a lot more water to stay happy. It all comes down to the plant's physiology, how it's built to deal with water stress. That said, even though plants are different, there's a generally accepted level of soil dryness, called the matrix potential, where most plants will start showing those permanent wilting symptoms. It's like a universal benchmark for when things get critical. Okay, let's talk about the other end of the soil moisture spectrum, field capacity. This is a really important concept, especially if you're thinking about things like irrigation. So let's break it down in a way that's easy to follow. Field capacity is basically the amount of water your soil can hold onto after it's been completely soaked, like after a big rain, and then left to drain for a while until the drainage slows way down to almost nothing. At that point, the soil is holding the maximum amount of water it can against gravity. Think of it like a sponge that's been soaked and then squeezed just enough so it's not dripping anymore. That's the soil at field capacity. When the soil reaches this point, most of the water in the bigger pores, called macropores, has drained out. The smaller pores, like the meso and micropores, are still holding some water, but they're not completely full. This balance is key because it's where the soil can still provide water to plants without losing too much to gravity. Here's why this matters for something like irrigation. If you add more water to the soil than it can hold at field capacity, that extra water is just going to drain away. It's basically wasted because the plant roots can't use it. So, overwatering past this point doesn't do your plants any favors, and you're just losing water. What's happening at field capacity is a kind of tug of war between two forces. the capillary forces that want to keep the water in the soil's pores, and gravity, which is trying to pull the water down and out. At field capacity, those two forces are in balance. They're at equilibrium. Now, some local experiments have shown that when soil hits field capacity, the matrix potential, which is a fancy way of measuring how tightly the soil is holding onto the water through capillary forces, is usually between 5 and 15 kPa. Interestingly, this range doesn't change much whether you're dealing with a clay soil or a sandy soil. The texture of the soil doesn't seem to make a big difference here, which is kind of surprising when you think about how different clay and sand are. So that's field capacity in a nutshell. It's like the sweet spot for soil moisture. Enough water for the plants, but not so much that you're wasting it. Let's dive into the concept of soil water and how it impacts plant growth. The amount of water in soil that plants can actually use is known as total available water, TAW. This is the difference between two key points: field capacity, FC, which is the maximum water the soil can hold against gravity after excess has drained, and the permanent wilting point, PWP, where the soil is so dry that plants can no longer extract water and begin to wilt permanently. TOW is a practical biological measure because it reflects how much water is truly useful to plants. Now, not all water in the soil is helpful. Water sitting in large pores, called free water, is often labelled excessive water. Why? It doesn't do much for plants. Instead, it clogs up the soil, reducing airflow and washing away valuable nutrients through a process called leaching. On the flip side, there's unavailable water, which is water held so tightly by the soil particles that plants can't access it, no matter how hard they try. Let's break it down with an example. I have placed a formula on the blackboard. TOR, that's FC, PWP. Say the field capacity is 0.25 cubic meters of water per cubic meter of soil, M3 and M3, and the permanent wilting point is 0.113 M3 M3. If the soil depth is 450 millimeters, the total available water works out to 54 millimeters of water that plants can tap into. The amount of water soil can hold also depends on its clay content. Soils with little clay, between 0 and 5%, can store about 60 to 100 millimeters of water per meter of depth. Bump that clay content up above 55% and the soil can hold as much as 160 millimeters per meter. More clay means more water holding power, which can be a game changer for plant survival. We've reached the end of our soil module, and I hope you now feel more confident about how soil, water, and plants interact. As you continue your path toward becoming an irrigation designer, the insights you've gained here will be invaluable, and soon you'll get to apply them in practical ways. But your learning doesn't have to stop now. In your PDF textbook, you'll find a collection of links to recommended readings and resources to deepen your understanding. Take advantage of them to keep building your expertise. Our final stop in this module is the quiz, your chance to ensure you have grasped all the materials we have covered. Before we wrap up, please take a moment to rate your experience by filling out the form. Your feedback helps shape this journey. Best of luck, and I'm excited to see you in the next module, where we'll explore crop-water relationships. Let's keep the momentum going.